You guys are amazing. Thank you for staying. My internet here has been unbelievably inconsistent. I just got booted. But we're back now, thanks to the miracle of cell phone hotspots. All right, I'm going to call and scream at Cox Cable.
Relatively expensive?
No, I mean, my T-Mobile plan at $35 a month includes it, but it sucks up data pretty quick. So I'll hit my data cap sooner than I would otherwise. It's all right. I don't know where I lost you guys exactly. I looked up as I was sketching this graph and realized you all weren't here anymore, which meant that I got booted. So let's return to where we were. I'm going to turn this off. So we're trying to find the surface area of the solid that's generated by rotating these parametric curves, or the curve generated by these parametric equations about the x-axis. In order to help us get a picture, we were eliminating the parameter t to see what sort of graph we had. We can solve the x equation here for t. Since x is equal to t cubed, we know that the cube root of x is equal to t. And then we take that and plug it into the y equation. Y is equal to t squared, which means y is equal to the cube root of x squared, which is x to the 2/3, which means that this parametric curve is a portion of the graph y equals x to the 2/3. Our time interval here was from 0 to 1. And when t is equal to 0, both x and y are equal to 0, which means our initial point is the origin down here. And our terminal point is the point associated with t equals 1. When you plug 1 into these, you get 1 for both. So the terminal point is 1, 1 up here. That means that my parametric curve is the bold portion of this graph. The whole graph here is x to the 2/3, y equals x to the 2/3. The bold portion of that, if you like with the orientation arrows here, is my parametric curve. So we're going to take this guy and rotate him about the x-axis. That's going to produce a kind of bowl shape. And this is what I'm trying to find the surface area of. Is everybody with me on this? Are there any questions about the graph or the solid generated by rotating that graph? I'm not rotating the whole thing again, just this portion. Okay. So our formula for the surface area of the solid is integral a to b 2 pi y ds, where ds is the little differential arc length form. So that's what we need to compute. I'm going to cover the picture. We're satisfied that we know what's going on now. So our surface area is the integral from a to b of 2 pi y ds. Y here, let's start with a and b. A and b are the endpoints of the time interval, 0 and 1. 2 pi is 2 pi. Y here is t squared. And ds is the square root of dx dt squared plus dy dt squared. So let's compute that. I'll compute the square of ds, just so I don't have to draw the big square root here right now. Dx dt is 3t squared. So this is 3t squared squared plus dy dt is 2t. So this is 2t squared. So my ds is going to be the square root of 9t to the 4 plus 4t squared times dt. So that's what goes in here. And this is my surface area integral. And there's a lot that we can do with this. I can pop out the 2 pi, extend over here. So I have 2 pi integral 0 to 1 t squared times, and within here I can factor out a t squared. In fact, I'm going to factor out a 4t squared under that square root. And then I'll be left with 9/4 t squared plus 1 dt. I can take the square root of these two pieces separately. And I get 2 pi integral 0 to 1 t squared times 2t squared, which is 2t to the 4 times the square root of 9/4 t squared plus 1 dt. And now I have to stop and ask, okay, how do I do this integral? We may end up going back a step because the only obvious move here is a trig sub, but that's going to be quite gnarly. So I'm inclined to think maybe there's an even better way to do it. We come back here, subbing for t squared, just a regular u sub, it wouldn't work out nicely. I would need an odd power of t here to make that go, so I could grab one of them to put with dt. If I tried to sub for the radicand here, I have a similar problem. The differential term won't work nicely because one of these t's would get eaten up by that. So I think really the only path forward from here is the trig sub. This is going to be pretty gnarly. Can you guys see what the trig sub should be? Okay, let's back up a step. Do we see how we got here? Are we comfy with the algebra steps that got us here? A little bit. So I force factored out the 4t squared. You see under here, we're factoring the 4t squared. If I were to redistribute this 4t squared, the 4's would cancel. So I'd have 9 here. And then t squared times t squared is t to the 4. And again, distributing this times 1 is 4t squared. So from here to here, I just factored a 4t squared. Everything else stayed the same. From here to here, I took the square root of these two pieces under the radical separately. I can do that because they're being multiplied. The square root of 4t squared is 2t. So that pops out. 2t times t squared. Oh, this is a t cubed. Okay, that's so much nicer. I'm glad we went back through that because I made an algebra mistake. The square root of 4t squared is 2t. All right, I'm coming for emphasis here. The square root of this piece, 4t squared, is 2t. 2t times t squared is 2t cubed. Everybody good on that? So I think I can make a somewhat simplifying assumption here by letting u be t squared. This would become 9/4 u plus 1. And this would become a 2u, and then one of these guys is going to get sucked up. So let me try this substitution here. Let's try u equals t squared, because then du is 2t dt. The bounds aren't going to change. When t is equal to 0, u is 0 squared, and when t is equal to 1, u is 1 squared. And those are 0 and 1 respectively. So the bounds stay the same through this substitution. So my integral will become 2 pi. Integral stays 0 to 1. I have 2t cubed here. One of those t's is going to get soaked up by the differential, as will the 2. Maybe I'll rewrite this as t squared times the square root of 9/4 t squared plus 1 times 2t dt, just to help everybody see where pieces are going and coming from. Now that 2t dt, that's du. And the other instances of t there are t squared, so those will just become u's. So this becomes integrals 2 pi integral 0 to 1 like this, which, while tricky, is manageable, not impossible. Who can tell me how to do this integral? We had a similar integral on exam 1. The challenge here is the radical, right? The reason why this isn't super easy is because this stuff is trapped under a square root and I can't distribute the square root. But notice that the thing under the square root is a linear function of u. So I'll make a second little substitution, and this hints that we could have done it all with one substitution if we were sufficiently clever. I let z be 9/4 u plus 1. And then dz is just 9/4 du. My bounds this time will change. U is running from 0 to 1, so those are my old bounds. When u is equal to 0, z is equal to 1. And when u is equal to 1, z is equal to 9/4 plus 1, which is 9/4 plus 4/4 is 13/4. So I get 2 pi integral 1 to 13 over 4. This u, I'm going to have to come back and solve this for u. I'll put in the square root first. This is the square root of z. And then du is 4/9 dz. And then if I solve my substitution for u, I get z minus 1 times 4/9 is equal to u. So that's what goes here. 4/9 times z minus 1. And this might look like it's a similarly challenging integral, but it's much easier because now I can write this as z to the 1/2 and distribute everything. I'll have 2 copies of 4/9 coming out, so that's 16/81. So I have 2 pi times 16, that's 32 pi over 81 times the integral from 1 to 13/4 of z minus 1 times z to the 1/2 dz. Now we can distribute and integrate. This is 32 pi over 81, integral 1 to 13/4 z to the 3/2 minus z to the 1/2 dz, and we are home free. So we get 32 pi over 81 times 2/5 z to the 5/2 minus 2/3 z to the 3/2. And we have to evaluate this between some pretty nasty bounds, 1 and 13/4. But that's not impossible. I'll give myself some more space. We have our 32 pi over 81. Any good offers from the other place, maybe? I'll have 2/5.
That teaches that you're not covered here, but I have this other company on the line. It's called. We start at $50 an hour. Sorry, $50 a month.
So here's what I get when I plug in my upper bound. And then we subtract from that what we get when we plug in our lower bound. When we plug in 1, this is just 2/5 minus 2/3. All right. So I apologize for the interruption. Even without the interruption, though, you see this is a fairly gnarly integral. So again, the sort of take-home message here is that arc length and surface area integrals, they're brutal. They really are brutal. Now, there might be a faster path, right? I think it's possible that you could have done the 2 substitutions here together. And there may even be a more clever route that I'm not seeing. Integrals tend to be like that. Sometimes there are long ways and short ways. 13/4 to the 5/2 and 3/2, those are horrible numbers. I wouldn't expect anybody to clean those up at all. So this would be sufficient. You can, of course, combine these if you want, but I would leave it like this. This would be fine. I promise on a test, I'll be curating the problems carefully. You won't have to evaluate absolutely horrible integrals on the test. I'm just looking to see that you understand the concepts and are able to handle the mechanics. This is surface area. And that was arc length. And they're rough. A funny fact is that the surface area integrals are often a little bit nicer than the arc length integrals. Because you have that 2 pi y out front, that'll often give you a piece that'll allow you to do u sub. Whereas the arc length integrals, you very rarely have such a piece and you need to proceed with trig sub. So as you work through the homework, you'll see an example or two where if you tried to set up the arc length integral, you couldn't do it. But if you set up the surface area integral, you can. And there are some really fun examples like that in the textbook also. I invite you guys to take a look at. Okay. It's about time for us to take our break, so we can do that. And then we will come back and talk about polar coordinates. The polar coordinate treatment is not going to be too intensive. We'll go through it fairly quickly, and I'll be pretty gentle on you, I promise, because I know we're short on time here. So we can take a break. We'll come back in, what is it? It's 1:59 now. We'll come back at, say, 2:10, and we'll talk about polar coordinates. Hey guys, we're getting back to class here in just a few minutes. I'm actually on the phone with the tech support people from my internet company right now. I think we're pretty close to having a tech scheduled to come out for like the fourth time this month. So if you guys could just be patient with me for 1 or 2 more minutes, I'll be right back to class. Be resuming probably around 2:15. Okay, lads and ladies, we are back. Sorry for the delay. I've got the Cox Cable tech support people on speaker, so if you hear some chatter in the background, that's what that is. I again apologize. It sucks that this is happening on the last day because it's such a fun opportunity for us to talk about so many cool things. But there are a few things that we need to button up and just get knocked out. So to focus on the stuff that you guys really need for the final, I'm going to go ahead and proceed to talking about polar coordinates. If you want to hang out a little bit after class, I do have some treats saved for today. Some really special, really cool things that I'm excited to show you guys. But first, just let's get the utilitarian shit taken care of. The last topic for this course is functions and areas in polar coordinates.
John,
Yes, ma'am.
I can have somebody out tomorrow, 10 to 12, 1 to 3, 3 to 5.
Earliest possible, please. 10 to 12 is good.
You want the phone number 941-356-4648?
That's correct.
Set for tomorrow between 10 and 12, and I did go ahead and credit that $100 total cost. So you'll see that show up on your next month.
Is there anything we can do about getting a refund for this last month where I've had absolutely shit service?
Give me 1 second.
Again, I don't mean to be rude. I know it's not your fault, but this is
No, you're fine.
All right, gang. So here's the idea. Polar coordinates, you may remember from trig, is an alternate way of thinking about points in the plane. Instead of specifying an x coordinate and a y coordinate, right? Instead of telling you how far to go east-west and telling you how far to go north-south, which is what we're used to get to this point right here, I could instead tell you how far out to walk along the horizontal axis and then how far up to rotate. Think about if you were sitting in class or you're sitting next to someone, you want to describe how to get from one place to another to a regular human being. We wouldn't normally say, go west 5 miles and then turn exactly 90 degrees and go north 2 miles. Normally you would say, okay, well, you're going to turn this much and walk this far. That's what polar coordinates are. So instead of specifying an x and a y, we specify a radius and an angle. So I call this angle here theta, and I call this distance here r. And the idea is you walk out r units along the x-axis, and then you rotate up by theta radians. Think of it as 2 different ways to give directions from the origin to this point right here. Polar coordinates are especially useful in situations where you have a lot of symmetry. If you have rotational symmetry, origin symmetry, those sort of things, oftentimes polar coordinates are the more convenient way to describe that point. So in Cartesian or XY coordinates, I would just call this the ordered pair x comma y. That's what we're all used to. In polar coordinates, I would call this r comma theta. So the first coordinate is r, is the distance from your point to the origin, and the angle theta is the positive angle you need to subtend from the x-axis to get up to that point after having walked out a distance r. Advantages and disadvantages of polar coordinates. Cartesian coordinates are unique. Every point in the plane has one ordered pair that tells you how to get there. Polar coordinates are not unique because I could walk around another 2 pi or another 2 pi and land back at this point. So while there's only one ordered pair xy that gets us to this point, there's actually infinitely many ordered pairs r theta that get us to this point. I'm going to look at some examples in just a second. Yes, ma'am.
Okay, so I've gone ahead and got everything situated. I did put the credit on the account for the month, so it looks like you only owe 96 cents. That's due on May the 4th. And you have the appointment set up for tomorrow. If you have it set up to get text alerts, you will get that. Or
Okay.
yeah, it looks like you have text and email alerts, so you'll get that notification here soon.
Thank you.
And I've also updated the ticket with what is going on. So when the tech comes out tomorrow, hopefully you'll see that there is a ticket in here.
Okay, that sounds good. Thank you so much.
Not a problem. I do want to thank you for calling back. I hope you have a great rest of your day.
All right, thanks.
Bye-bye.
Holy shit. All right. Fuck Cox Cable. So if I give you the Cartesian coordinates for a point, can you find the polar coordinates? there's, like we said, more than one set of polar coordinates for this Cartesian point. The trick to going back and forth from one to the other is to come in here and actually find a little right triangle. I'm going to draw it in blue. So you see here this bold blue right triangle. We can use some very basic trigonometry to express r and theta in terms of x and y. Think about the definition of sine and cosine. Sine theta is the opposite over the hypotenuse. So for this angle theta in here, the sine of theta would be this vertical length over this hypotenuse. Well, this vertical length is the altitude of that point, which is y, and the hypotenuse is the radius, r. So sine theta is y over r. And I can solve that for y. That means y is equal to r sine theta. Similarly, cos theta is equal to x over r. Cosine is the adjacent over the hypotenuse. The adjacent side length here is the base, which is x. It's the horizontal distance from the origin to that point. And the hypotenuse is again r. So if I solve this for x, I get x equals r cos theta. And then the last thing we need, there's really two other things I should say. By Pythagoras, x squared plus y squared is r squared, right? That's a squared plus b squared equals c squared just for this triangle. And the other thing we get here is that the tangent of theta, if I look at the tangent of this angle, that's the opposite over the adjacent, that's y over x. So this is sort of my key, right? Like a map key to go back and forth from one to the other. The dictionary that allows me to go back and forth from Cartesian coordinates to polar coordinates. You need to remember these equations. X squared plus y squared is r squared. Y is r sine theta. X is r cos theta. And the tangent of theta is y over x. So these four things are the key to going back and forth from Cartesian coordinates like this to polar coordinates, which is what we want. So let's see if we can find the polar coordinates for this Cartesian point. I'm going to redraw the picture down here. I'll call this 2, and I'll call this 1. So my Cartesian point is right here. I need to find r and theta. Theta is this angle, r is this distance. The first item in our key, x squared plus y squared equals r squared, will tell me how to find r. This means 2 squared plus 1 squared equals r squared. Now 2 squared is 4, 1 squared is 1, so this is 5 equals r squared. So r is 1 of plus or minus the square root of 5. We could use either. I'll tell you how to handle negative radii in just a second. Let's focus on finding the polar coordinates here where r is positive. We'll use r equals the positive square root of 5. What about the angle theta? also, we know that the tangent of theta is equal to y over x. Well, y here is 1 and x here is 2. So the tangent of theta here is equal to 1/2. And of course, there's infinitely many angles theta that satisfy that because tangent is periodic. But I can find the smallest positive angle that works. That's sort of the most natural choice. So what is the smallest positive angle theta such that tan theta is equal to 1/2? Well, that's the inverse tangent of 1/2. It's not a super nice number. We can approximate it as a decimal in radians or degrees if we want. If I ask for the inverse, there. If I ask for the inverse tangent of 1/2, my calculator is currently in radian mode, so this is about 0.464 radians. Or if I want it in degrees, I get about 26.57 degrees. Now we usually work in radians, and I would just leave this as the inverse tangent of 1/2. So the polar coordinates for the Cartesian point 2, 1 are, I'll write it as r comma theta equals, my radius is the square root of 5, and my angle is 0.464 radians. Or we could just call this the square root of 5 comma the inverse tangent of 1/2. So going from Cartesian to polar is not bad. You have to find your radius. And to do that, you use the x squared plus y squared equals r squared stuff. And you have to find your angle theta. To do that, you use the fact that tan theta is y over x. Not bad. Going the other direction is even easier. If I specify the polar coordinates, you can find the Cartesian coordinates just by plugging stuff in to these relations. If you know r and theta, you can plug into these to get x and y. Let's see what that looks like. So to find the Cartesian coordinates, for the polar point, r comma theta equals, let's do 2 comma 2 pi over 3. I find it helpful to draw the picture. So I want to walk out, I'll call this 2 units. The horizontal axis here is called the polar axis. So I walk out 2 units along the polar axis, and then I rotate around by 2 pi over 3. So if I rotate this around by 2 pi over 3, I will get over here. So this radius is 2. This angle here is 2 pi over 3. So here is my point. We can see from the picture that x should be negative and y should be positive. And finding the coordinates is as easy as plugging in. So you know that x is r times the cosine of theta. R is 2 and theta is 2 pi over 3. So this is 2 times the cosine of 2 pi over 3. What is the cosine of 2 pi over 3? Anybody help me out with that? Think about your unit circle. I think negative root 3 over 2 would be the cosine of 5 pi over 6. I think we're not quite that far.
-1/2.
Yeah, negative 1/2. So this is 2 times negative 1/2, which is negative 1. But that root 3 over 2, that's going to be important here in a minute, because y is r times the sine of theta. And again, r is still 2. They're refunding us for the last month of service. And sine of 2 pi over 3. So the sine of 2 pi over 3, what is that guy? So 2 pi over 3, remember, is over here in quadrant 2. So the signs are all positive, but you're correct that it is the square root of 3 over 2. So this is 2 times positive root 3 over 2, or just the square root of 3. So the Cartesian coordinates of this point are x comma y equals negative 1 comma the square root of 3. That's all right, don't feel bad. So going back and forth from polar to Cartesian, Cartesian to polar, it's not bad. There's one subtle thing I want to show you about going from Cartesian to polar, and that's to do with the non-uniqueness, which also has to do with the possibility of the radius being negative. So just for fun, I want to plot the polar point. I'll give a few of them. Plot the polar points. We'll do 1 comma negative pi over 4. We'll do 2 comma pi. Let's do negative 2 comma pi. And negative 1 comma pi over 3. So I'm going to show you here how to understand negative radii. First, we're going to get some practice just plotting these things. That's fine. But then parts C and D, I'll show you what to do with your negative radius. All right. To get to 1 comma negative pi over 4, I'm going to mark this as 1 and this as 2. To get to 1 comma negative pi over 4, I walk out 1 along my polar axis, and then I rotate down by negative pi over 4. So that's going to land me right about here. This is 1 comma negative pi over 4. To get to 2 comma pi, I'm going to walk out 1, 2 along my polar axis, and then rotate around by pi. So that's going to land me right here. This is the polar point 2 comma pi. We walk out 2, and then we rotate pi in the positive direction. There's 2 ways to think about how to get to -2 comma pi. I'll graph these separately down here. The way that I find most people really like is instead of walking out on the positive horizontal axis, you start by walking out on the negative horizontal axis. So again, I'll mark this as like 1 and 2. So this would be like 3, right? So this would be like -1 and -2. You could walk out to -2 along the polar axis and then rotate in the positive direction pi. So it turns out that this point right here is -2 comma pi. And you see some symmetry between these guys, right? That's the other way. The other way you do this is by plotting the point +2 comma pi and then reflecting over the origin. So -r comma theta to get to find -r comma theta, plot r comma theta, and then reflect through the origin. So 2 comma pi we said is right here. If I reflect this point over the origin, I land back here. So this guy, again, would be -2 comma pi, right? And you get to that same place regardless of how you do it. You can walk out -2 along the polar axis and then rotate pi, or you can locate the point +2 comma pi and then reflect it over the origin. Let's see if we can find -1 comma pi over 3. Those 2 ways. First, I could walk out -1 along my polar axis. So instead of going out this way, I go out this way, and then rotate in the positive direction pi over 3. That's 60 degrees. So that's like here. Not distant. Yeah, right about here. So this would be -1 comma positive pi over 3. The other way to do this would be to locate +1 comma pi over 3, which would be right about here, by going out 1 and rotating up pi over 3, and then reflecting that over the origin. That's how this stuff works. So if your radius is negative, the way I do it is the second way. That's the way I was taught. And that's the way that I like, because it exploits symmetry. So if I want to find -1 comma pi over 3, first I find +1 comma pi over 3 and reflect it through the origin. But the alternate way works also. You could just go out on the negative polar axis and then rotate. Either one works. The reason this is so important is, one, because of non-uniqueness. You need to be able to tell whether 2 polar points are sending you to the same place or not. The other is graphing polar functions. And that's where we're going to go with this. But first, I'm going to do one more exercise where we play with these. Are there any questions about how we plotted these points? I'm going to recharge my coffee and we'll look at some more. Okay. Huh. So now that we know how to handle positive and negative radii, I want to find three representations, three polar representations for the Cartesian point let's do, I don't know, 7, 14. So I want the polar coordinates. I have here X and Y. I need to use that key. I know that X is R cos theta. Y is R sine theta. X squared plus Y squared is equal to R squared. And the tangent of theta is equal to Y over X. It's these bottom two that are going to be useful here. Because we have the Cartesian coordinates, we want the polar coordinates. So I want R and theta, and those are the easiest ones to solve for R and theta. X squared plus Y squared equals R squared. In this case means 7 squared plus 14 squared is equal to R squared. 7 squared is 49. I'm not sure what 14 squared is off the top of my head. It's 4 times 49. I'll just use the calculator. We get 196. So the sum of those is 245, and the square root of that is 15.56. I'll just write it as the square root of 245. So R is 1 of plus or minus the square root of 245. And here, I'm going to find one of the polar representations using the negative radius. Now, before I can do any of that, I need to also find some thetas that might work. So we know that the tangent of theta is equal to Y over X, which in this case means tangent of theta is 14 over 7, which is 2. So theta is the inverse tangent of 2. And if you want, you can get a feel for this in degrees. I think I'm still in degree mode, right? Yeah. So the inverse tangent of 2, come here, it's about 63 degrees. We'll call it 63.4 degrees. If we want to work in radians, we would just leave it as the inverse tangent of 2, but to draw it, it's helpful to have some feel for the size. So let's plot this thing. I'll call this 7, and I'll call this call this 14. So here's my point. And I claim that one of the ways to get there is to walk out the square root of 245. this distance, and then rotate up by the angle theta, which is the inverse tangent of 2, or about 63.4 degrees. So one polar representation for this point would be the square root of 245, comma, inverse tangent of 2. This is one answer. But I said I want to find 3 of them. One way to do this is to run through that exact procedure, right? Walk out root 245, rotate up arctan of 2, and then spin around another 2 pi. So the simplest form of non-uniqueness here comes from the modulo 2 pi stuff. In other words, I'm talking about the point root 245, comma, arctan 2 plus 2 pi. Or if you're using degrees, it would be 63.4 degrees plus 360 degrees. So here is a second representation for that point. A third representation for that point, if I wanted to, I could use the negative version of that radius. That would be negative root 245. Now this point right here would be negative root 245, comma, arctan 2. It's the point reflected through the origin. So if I want to get back around to here, I would have to add pi, or add 180 degrees, inverse tangent of 2 plus pi. And this would be a third representation of that same point. So these are 3 different polar representations for the Cartesian point 7, 14. Are there any questions about where I'm getting any of these from? Be mindful that I could ask you to do this on the final, not just on the take-home. Okay. In the remaining bits of time we have here, I want to show you some polar functions. It looks like we're a little short on time. I was expecting this, so this is where our supplemental lecture is going to come from. I will record it as soon as I can, hopefully this evening. If not this evening, tomorrow morning at the latest. But I want to show you some graphs of polar functions, and then I'll give you the formula for the area stuff. So if you want, you can just grind ahead. So graphing polar functions. These are usually of the form r equals some function of theta. But not necessarily. They could also be of the form theta equals some function of r. Just like Cartesian stuff can be y equals f of x or x equals f of y. Best way to do this is to look at some examples. A constant function, r equals 3 in polar coordinates. You can make a table. Theta and r. If theta is 0, r is 3. If theta is pi over 4, then r is 3. If theta is pi over 2, then r is 3. If theta is pi, then r is 3. You get the idea. It's a constant function. So no matter what you plug in for theta, you always get 3 out for r. Theta was 3 pi over 4, r would still be 3, and so on, right? All of these. So if I plot those points in polar coordinates, theta equals 0, r equals 3. I'll call this 1, 2, 3. Here's the polar point, theta equals 0 and r equals 3. The polar point with theta equal to pi over 4 and r equal to 3 would be right around here. We always list the r coordinate first. So this would really be 3, 0. This would be 3, pi over 4. The polar point where theta is pi over 2 and r is 3 would be up here, 3, pi over 2. You can kind of already see what's happening. 3, 3 pi over 4 would be over here. I'm trying to draw it symmetric. 3 pi over 4, 3. Pi, 3 would be right here. Or sorry, 3, pi. So if you look at these points, you can kind of see what would happen. Let me fill in the other multiples of just pi over 2. We've got 3 pi over 2 and 2 pi. At each of those, the radius would be 3. So 3 pi over 2 is down here. The polar point 3, 3 pi over 2 is right here. So what is this? There would be another point like here, another point like here. What is this curve? Again, modulo my bad art. It's a circle. So curves like r equals a constant, this will always be a circle of radius r centered at the origin. The other kind of fun introduction things like this that I do in trig when I teach these things is I look at theta equals a constant. So let's look at the curve theta equals pi over 4. These are sort of the simplest possible things. Again, I can build a table. R equals a constant is like the equivalent of a horizontal line. So horizontal lines in Cartesian coordinates kind of turn into circles centered at the origin in polar coordinates. Theta equals a constant in polar coordinates is kind of the polar equivalent of x equals a constant, which are vertical lines. Let's see what that gives me here. Again, I'll make a table with theta and r. No matter what I choose for r, if r is 0, theta is pi over 4. If r is 1, theta is pi over 4. If r is -1, theta is pi over 4. If r is 2, theta is pi over 4. You get the feeling. And if I wanted to graph this guy, no matter what radius I'm looking at, my angle is always pi over 4. So here's the point 0, pi over 4. I mark this as like 1, mark this as like 2. The point 2, pi over 4 would be, let's see, 1, this would be like right about here. This would be the point 1, pi over 4. 2, pi over 4 would be right about here. What about -1, pi over 4? Well, that means I would go out -1 and then rotate down by pi over 4. That's going to get me right here. So this is a line. This is a line through the origin, making angle pi/4 with the polar axis. This is the graph. So if your polar function is theta equals a constant, this will be a line through the origin making that constant angle with the polar axis. Remember, the polar axis is the name for the positive x-axis in polar coordinates. This guy. So these are your two simplest things. I'm going to show you one or two more, and then I'll let you guys go. I know we're over time. What about a linear function? What about just like r equals theta? What if I want to sketch this? Again, like we're back in algebra or trig, we make a little table. Theta and r. If theta is 0, r is 0. If theta is pi/4, r is pi/4. If theta is pi/2, r is pi/2. You get the idea. If theta is 3pi/4, r is 3pi/4. If theta is pi, r is pi. This is sort of the equivalent of y equals x, but in polar coordinates. Y equals x in Cartesian coordinates is a line, but this is not going to be a straight line. To help us out, let me get a feel for the size of pi/4, pi/2, and so on as decimals. Pi/4 is a little smaller than 1, call it 0.8. Pi/2 about 1.6. 3pi/4 it's about 2.4. And pi, of course, is like 3.1. So as theta increases, r increases. This is actually a curve we saw earlier today. We saw this curve when we were talking still about parametric equations. Here's the polar point 0, 0. To get to the polar point where r is pi/4 and theta is pi/4, I'll mark this as, this is 1, this is 2, this is 3. I walk out pi/4 and I rotate up pi/4. So walking out pi/4, that's like 0.8. And then rotate that up pi/4. So here's the point, the polar point, pi/4, pi/4. Pi/2, pi/2, this guy, I walk out like 1.6, that's like here. And then I rotate up pi/2. So what's that? Like here. Three pi/4, 3pi/4, I walk out about 2.4 units, that's like here. And I rotate all the way around 3pi/4, which is like to here. So we're going to be out right around here. And then pi, pi, so do I have room to get it here? pi comma pi would be like right here. So this was the polar point pi comma pi. This was the polar point 3 pi over 4 comma 3 pi over 4. This is the polar point pi over 2 comma pi over 2. This is the polar point pi over 4 comma pi over 4. And of course, this is the polar point 0 comma 0. If I connect these, can you see what this is going to produce? As theta increases, r continues to increase. It's going to be that Archimedean spiral. It's in fact the same Archimedean spiral we saw before, increasing at unit speed. So this is Archimedean spiral. Now, what I'm going to be showing you guys in the supplemental lecture that I will record tonight is how to find areas like these. And that's the very last thing in this class. I'm also going to show you how to graph more polar functions. I'm going to give you some more examples because there's really a few families of important things, like you need to know parabolas and basic polynomials to do algebra and Cartesian coordinates. There are some basic things like other circles, cardioids, limicons that you need to know in polar coordinates. So I'll show you in the supplemental lecture how to graph more shit, but also how to find areas. And for those who remember how to graph more shit from trigonometry, I can give you the recipe for these areas. So the area bounded by the polar curve r equals f of theta from theta equals alpha to theta equals beta. I'll include the derivation of this in the lecture. We integrate from alpha to beta 1/2 of f of theta squared d theta. You can write this more kind of succinctly as integral alpha to beta 1/2 r squared d theta. Either formula is a fine way to remember it. I prefer the second one, but either one is okay. So I'll let you guys go. I know you got shit to do, but this is the recipe you would follow to calculate areas. I'll show you how to graph some more stuff in a video that will show up later tonight. And that is the end of Calc 2, guys. It's really, really good stuff. It is. I can't emphasize enough how beautiful, especially the power series stuff is. One other thing to kind of whet your appetite. So the supplemental lecture video tonight will contain 1 more polar graphing. 2 areas in polar coordinates. And 3, a proof that e to the I pi really is -1. This is an insane statement. It's beautiful. It's really quite amazing. In fact, what we're really going to prove is that e to the I theta is cos theta plus I times the sine of theta. And believe it or not, this thing has a magical way of connecting complex numbers, power series, and polar coordinates all into one thing. A consequence of it is this e to the I pi equals -1. You plug I pi in for theta here, it'll come out right away. Sorry, you just plug in pi for theta here, it comes out right away. Other cool stuff this will let you do is let you take natural logs of negative numbers. That's something that was thought to be impossible before. So it turns out power series are the key to getting really cool shit like this. This was called Euler's formula, or Euler's theorem, and it was one of the big breakthroughs that allowed modern electrical engineering to do what it does. Also a big deal for contour integration and things like that. The last few things I want to say to you here, your take-home test is ready. I'm going to publish it to Canvas right after we finish this. I have cleared out extension requests in WebAssign. I will do that one more time this semester. So if you need something open in WebAssign, you want to go back and earn some points, put in that extension request right after class. So as soon as class ends, I'm going to post your take-home test. I can show it to you briefly. I haven't actually finished making all the updates I want to make yet. Here it is. So this is going to be your take-home test. I'll post instructions for this. You're going to print it. You're going to read these instructions. You're going to sign this honor pledge down here, and then you'll answer the questions. Like I said, I haven't quite finished updating it. I'm going to get it done here in the next few seconds, and then post it for you. That is going to be due on the day of your final. And you will have until 11:59 on the day of the final to turn that in. Your final is on the 27th, which is next Tuesday. So I'll get that posted. If you want anything open in WebAssign, please make the extension request now. I will do that right after I polish up your exam 3 and post it. And that's it from me, lads and ladies.
Is the final going to be online or is it going to be in person?
Yeah.
The final?
Yeah.
It'll be on Canvas. It'll be just like our midterms.
Okay. Okay.
Same.
So we'll have to have like a little Zoom setup with the, you know, the
Yep,
analog as
we'll
well.
use
Okay.
Zoom and analog. All the things will be the same. I don't want to change that up on you guys here for the last thing.
Okay. Do we have any study guide for the final or any stuff like
No
that?
separate study guide for the final. Well, actually, let me see, because we did exam 3 as a take home. I don't want to overwhelm you guys. Let me think. You've got plenty to do. So probably what I'll do, maybe either nerf the last study guide grade, or I could put out an extra assignment. Let me think about that a little bit. Okay, my brain's a little bit frazzled right now, but I'll post an announcement. I don't think I want to give you guys that extra work. You've got plenty of work right now. So to prepare,
Mostly I'm just worried about being prepared for the final and being prepared for this take-home exam.
right, of course. So to make sure you're prepared for the final, first make sure you do all the homeworks, right? If there's any homework that you haven't knocked out or understood entirely, even if you have done it, like done it all, put in answers. If there's any homework that you're uncomfortable with, please request an extension in WebAssign so I can pop it. You can go back in and play with things between now and the final. And then go over the midterms. So the questions on the final are going to be similar in spirit to the questions on the midterms.
Very exciting. All right.
All right. Anything else you guys are dying to know here?
Yes, I have a question.
So Alejandro, I don't, I'll need to think about what I want to do for study guide 3. On the one hand, I don't want to rip you guys off for points. I know you guys count on those study guides to bring up the average a little bit because the tests are hard. But on the other hand, you've got lots to do between now and the final. So let me think about it a little bit. I'll post an announcement about the study guide when I post the extra video later tonight. Lydia, what was your question?
Sorry, I just wanted to double check. So the exam 3, it's not an honor lock test, it's a paper test, the take-home test, I mean.
Correct.
So is there any sort of proctoring that we need to use, like while we take this paper? Like, do we need to record ourselves? Do we need
No, you don't.
Nope. No, you just work the problems on your own, scan and submit your solutions.
Yeah.
There's an honor pledge there. Basically, there's not a whole lot. I'm writing the test in a way so there's not a whole lot that you could do to get help, but I'm also counting on you guys to please just be honest. I'll find out on the final if you've got those skills or not. And to save you the stress, it's just going to be like, think of it as like a worksheet, but you need to work it on your own. You need to work the problems by yourself. Sharing, duplicating, talking about any of the questions definitely counts as an honor code violation if I find out about that stuff. And it has happened in the past that I found out students talked about take-home tests. I will start a conduct trial over it. So please just be honest, work the problems, submit them. Nope, not timed. It's just due by midnight on the day of the final. So
Is there any way to
and you have to upload
sort of work on it electronically? Because I know that some of us may not have access to a printer.
I would very much prefer that you print it. So we've got a few days. There's time to find a printer and print the thing. But if you absolutely cannot, then you can copy the questions down onto paper and give me your handwritten version, but I would much prefer the printed thing. I'll be able to grade it a lot faster if we print it.
Okay.
Kyle asked if the take home is timed. No, the take home is not timed. The final, however, is timed. The final is a 2-hour proctored test.
Professor, I have a question.
Sure.
That is the only day that we can take the final exam?
Unless there is some extreme circumstance, then
Yeah, because that day I have my final exam also for chemistry 1, and I will have like 30 minutes only to like from one exam to another one.
So a few people have contacted me about the Chem 1 conflict, and I've been emailing with the Chem 1 professor, and he said that he moved his final. Right, so let me,
Okay.
I'm going to turn
Okay.
off.
Maybe I will talk with my professor too, because my exam from you is from 1 to 3, and from chemistry from 3:30 to 5:30. And that will be a problem for me because.
1 second. Let me see. I'm digging through my email now.
Okay, thank you so much.
So I did email with him. Conflict between chemistry. I've not seen any other communication that was resolved. What's the guy's name? Larry Chamusko, right? So everybody who has the chem conflict, are you all in Chamusko's class?
Sorry, what you say?
Your chemistry professor, is it Chamusko, Larry Chamusko?
No, it's Tina Beck.
Oh, okay, that's a problem. All right, so if you, shit, you guys all have different teachers. Okay, if you have a conflict with the chemistry final or any final, send me an email, CC your chemistry professor. Don't use Canvas, use email. Send it to me and include your chemistry professor as a CC. Yeah, I see at least 4 different professors now who have conflicts. This is a real problem. So
Is it an issue if they're like
email.
30 minutes apart? Because
No, that's normal, right?
Yeah,
If you
okay.
have an actual overlap, then that's something we need to fix. If you have one final after
Yeah,
another, it sucks, but that's life sometimes. You can talk to
Yeah,
your other
the
professors,
problem is
they'll help.
because I will take your exam in my home, and my final is in my final of chemistry 1 is in Santa Fe.
Hmm.
I'm in the same boat as Sebastian. I kind of have to race over there as soon as I get done with yours.
Same.
Okay, well, so options to help with that, you could take my final in the library, right? You don't have to take it at home. You could go to campus and take it on campus. They'll accommodate you there, or in the testing centers, right? The testing
Yeah, I
centers.
talked to my professor and he was like, it's okay if you're a little late.
Okay, so if you have a conflict, whether it's an actual overlap with testing time or an issue with transportation, do me a favor, email me and your professor, one email, both of us in the recipients, and let's get it all sorted out. As long as everybody talks to each other and we all know what's going on, I can try to be flexible, but the general rule here at Santa Fe is that Nat Sci bends for math. So if there's a conflict between a Nat Sci and a math final, Nat Sci is supposed to accommodate math. I understand right now with the Zoom stuff, it's a little bit weird. Those of you who don't have a time overlap with the final, but just have kind of an unpleasant rush between one and the other, see if you can schedule space in the library or at the testing center. I can schedule for you at the testing center if they give you trouble there. But let's try to get this sorted out. Send me an email, CC your chemistry professors or physics professors, whichever one has a conflict, and we'll get it knocked out before the weekend, okay? All right.
Thank you so much.
Of course, of course. Okay, guys, I'm gonna go ahead and end the class here. I hope you all have a lovely rest of your day. Watch for that video. It'll pop out probably 7, 8, 9 p.m. tonight. And then I just want to say it's been a real pleasure. Thank you guys all so much for the work you've put in. I know this is a hard class. I know it requires a lot of time and effort on your behalf, and I'm really proud of you for putting in that time. So I wish you all luck on your finals, including ours, and I will see you on Tuesday, if not sooner.
All right. Thank you very much, Professor.
Thank
and
you.
Also, are there going to be
Yes.
office hours between now? Okay.
Yep, office hours will continue as normal until next Thursday.
All right. See you later, Professor. Thank you so much.
Thank
And
you.
have a great day.
Take care, guys.